Share screen. All right, so ideally, today will be the last day of NSOP1. We will conclude the proof that Kim independence is symmetric, and that will be sort of like our indication that Kim independence in some way is like the appropriate notion of independence to study when you want to study NSOP1 structures, provided that your goal is to generalize non-forking independence in the simple theory. So if you recall, when we studied non-forking independence in the simple theory, we proved several things. We proved Chem's lemma, symmetry, Kim forking equals Kim dividing, and we proved the independence theorem. So all of those things are very nice and useful. And so we want to generalize those to a broader context, working with perhaps a weaker independence notion, and that's ultimately what we'll do. So we won't have the time, sadly, to prove the independence theorem, but we'll do symmetry and then we'll move on to NTP1, so everyone will get a kind of taste. But nonetheless, I think like what we're doing now is this construction of Morley trees, and that is really like at the heart of the theory. So if you understand that inductive construction, then you'll understand the basic ingredients for the rest of the theory. All right, so let's just remind ourselves of the tree. I think that's the thing that will be easiest to forget. So let's get started there. Right, so we have an ordinal alpha, and we look at the set of non-limit ordinals in alpha. So that's NL of alpha. That's the starting point. And then we let T alpha be the functions which are valued in omega, whose domain is an in segment of alpha beginning at a non-limit and whose support is finite. So those are the three conditions. It's omega valued, it's defined on an in segment of alpha that begins at a non-limit, and it is a finite support. So those are the functions that you look at, and that functions like a tree under inclusion of functions. And we saw when you take the index of the tree to be a natural number, the associated tree that you get just looks like omega to the less than or equal to n. It's a familiar thing. The thing that changes is when you take the index of the tree to be infinite, and then you get some ill-founded tree. The reason being that finite ordinals are the ones that are well ordered both ways. That's the unique property of a finite ordinal. And because we're looking at n segments, you're going to get something ill-founded when you allow infinite domains. So that will sort of explain itself naturally just by looking at the proof. The proof of trees indexed by T alpha will naturally sort of produce these index sets, which sounds strange, but you can sort of see how to get T1 to T2, how to get T2 from T1, for example. What do you do? Well, one way to think in your head about how to get T2 from T1 is I take T1, and then I take infinitely many copies of T1, and then I add a new node at the bottom. So if I think about this as T1, then I can take countably many copies of it, and then add something new at the bottom, okay? And what happens if I iterate that procedure countably many times and then take the union of the tree that I built? Well, at each step, I'm adding something new at the bottom. So of course, I'm going to end up with something ill-founded. And then you can just check that if you just do this procedure and then at limits take unions, what you'll get is this family of trees. So we're going to do something where we take countably many copies of the tree that we've built so far, add something new at the bottom, and then we see where that takes us, and lo and behold, it takes us to these things. And just to remind you, we had a few different notations that we associated with this tree, the first of which was the canonical inclusions. This tells me how to take the T alpha tree and put it inside the T beta tree. And what I do is I just sort of extend by 0. So I have a function which is defined in an segment of alpha. I want to get a function which is defined in an segment of beta. How do I do it? Well, on all of the new elements of the domain, I just make it 0. And that puts T alpha into T beta by setting it sort of on the all zeros path. Great. The second thing is the all zeros path, which is the functions that are identically zero. And the important thing is just to note that we fixed a name for that, which is zeta beta, which is the particular node on the all zeros path that begins at beta. Okay, we have concatenation, which makes sense. I mean, intuitively, you know what this looks like. You have your tree, you have a node eta, and then you add an I on top. That's eta concatenated with I. And you just have to think for a minute how that should look set theoretically. And okay, if you have a function whose domain is beta plus 1, then the thing that's on top of it now should have domain starting at beta. So you define the value at beta to be I, if you want to define eta concatenated with I. Likewise, if I'm given eta in T alpha and I want to define I concatenated with eta, I want to add one new element at the bottom. So if my in segment was from something all the way to alpha, now I want an in segment of alpha plus 1. And what am I going to do? I'm going to define it to be I at alpha. So those are the two ways of extending by 1. I can either extend it at the top, in which case I need to make my initial segment start a little, or sorry, my in segment start a little bit earlier, or I want to add something to the bottom, in which case I extend my in segment at the end. So those are the two choices, and that makes sense. So these are ways of set theoretically cashing out what is sort of intuitively obvious. If you have, eta concatenated with I, then you put an I on top. So as long as you understand the picture, then you're in good shape. Okay, so we argued that T alpha index trees have the modeling property. We didn't actually prove this, but we sort of justified it by saying that we know that this is true for S indiscernible trees with the normal language. And then you can sort of check just by compactness that if you know that it's true for the LS, the language of S indiscernible trees, then it will follow when you add more predicates. That doesn't actually change the situation. There's a slight check there that we haven't done, but it's a very easy argument just using compactness. And then we had this notion of restriction, which is, I think, the last notion that I have to introduce, which just says what it means to look only at a few given levels of a tree. And what do? You look to zoom in at a few levels of the tree. You look at those nodes in the tree whose domain begins at one of the sets in question, and you look at the nodes that are 0 on all of the levels outside the set in question. So you can only be non-zero at elements in your set, and you insist that you're only looking at the nodes whose domain begins at an element of that set. So that's like zooming in at a few levels and just looking at the nodes that have non-trivial behavior on those levels. And last time we talked about how if you take such a set, let's say it's finite of size n, then if you restrict T alpha, for any alpha in fact, to that set, you'll get something that looks like omega to the less than or equal to n, take away the empty node. Okay, so it's not exactly a rooted tree, but it's a tree. Good. Okay, so the reason that we introduced this restriction idea is that using Erdos-Rado, you can, from a very large tree, find one where not only are you S indiscernible, which tells you that you can move sort of horizontally, but you can no longer distinguish between the levels. So this is like what we called a strongly indiscernible, a STR indiscernible tree before. So if you recall, the STR language was one where you have the tree partial order, the binary mean function, and the lexicographic order, and this pre-order that compares the levels. So there, if something happens here, it also happens here. And what we're doing is we're sort of doing exactly the same thing. But the reason that we needed Erdos-Rado kind of theorem for this, instead of just using the theorem that we had before that said that STR indiscernible trees have the modeling property, the reason that we have to do this is because we care about preserving the type. We need it to be based on, not just locally based on. And this is sort of like the same basic reasoning for why when you're doing simple theories and you want to construct Morley sequences, you need to use Erdos-Rado instead of Ramsey's theorem. So it's because you care about preserving more. You care about preserving the type, not just the behavior of individual formulas. Okay, so these are kind of subtle points that we don't need to dwell on too much, but that's at least the motivation. Okay, so now we're coming to the definitions that talk about model theory, really. I mean, up to this point, we were really just sort of talking about a set theoretic object. So the first thing is spread outness. So what does spread outness say? It says that if you fix a node and you look at the successors of that node and the cones above them, those cones are a Morley sequence in some M-invariant global type. So a tree is spread out if whenever you take a node that is not at the top of the tree, then the sequence of cones above it forms a Morley sequence in some global M-invariant type. So you can think of it as spread out horizontally. And here we have a picture. I fixed some eta. I've looked at all the cones above them. And that sequence of cones is a Morley sequence in a global M-invariant type. Okay, so that's what it means to be spread out. And so a Morley tree is just a tree that is spread out, S indiscernible, and also has this vertical moving property. Another way of saying this is that a Morley tree over M is just an STR indiscernible tree, which is spread out. Because condition B and condition A together imply that the tree is STR indiscernible. But we don't want to just apply the modeling property for STR indiscernible trees because you have to preserve more. Okay, so now a tree Morley sequence was defined to be a path in a Morley tree. And now what we want to do is we want to construct those. That's sort of where we've arrived. And last time we showed that, okay, if you're a Morley tree, if you're a tree Morley sequence, then in particular you're a Morley sequence with respect to Kim independence. But those things are not the same. Cool. So now let's try to do our main existence theorem, which is going to tell us that these things exist. And we need to prove just a little bit more than that they exist. But in fact, if I have a model of my theory T, and I'm given two tuples, A and B, which are Kim independent over the model, then what I want to be able to prove is that I can find an MB indiscernible tree Morley sequence over M starting with A. And then I will combine that with a proof that tree Morley sequence is witness Kim dividing, and then I can replicate the proof of symmetry in simple theories. So maybe this is a good point just to sort of hold the argument in your head for reminding ourselves how the proof of symmetry in simple theories goes. So let's suppose that we're working now in a simple context, and I want to prove that forking is symmetric. So what do? I assume that A is independent with B, and I want to switch. I want to say that B is independent with A. So from the assumption that A is independent with B, I use extension a whole bunch of times to build a sequence of elements that all have the same type as A over B, but which have the property that AI is independent with A less than I and B for all I. So I make it very long that has that property. So when I apply Erdős-Rado and extract a sequence, I get something which is MB indiscernible and Morley over M starting with A. But then Kim's lemma tells me that if I have a Morley sequence starting with A, which is MB indiscernible, then B has to be independent with A. Because if it wasn't, then there would be some formula in the type of B over A, which is inconsistent along that Morley sequence, and that's incompatible with it being indiscernible. So we want to try to replicate exactly the same argument. The problem is that Kim independence is defined to be the dividing that is witnessed by invariant Morley sequences. And if I know that A is Kim independent with B, that tells me that A and B are independent in a very weak sense. Saying that A is invariant independent with B, which is what I need in order to construct an invariant Morley sequence that is MB indiscernible, that's a really strong form of in independence, which is not necessarily guaranteed to me by this hypothesis that A is Kim independent with B. So what we want is to try to somehow wiggle out of this rock and a hard place. We want to construct a sequence which is generic enough to witness Kim dividing. So it looks like invariant Morley sequences and that it's very generic somehow, but at the same time is not so generic that it doesn't exist just when A is independent with B over M in the sense of Kim independence. We need it to be somehow weak enough that it'll exist under this hypothesis, but strong enough that it will still witness Kim independence in order to replicate the argument for symmetry that we saw in simple theories. So that's where we're going. And okay, how do you construct a tree Morley sequence? Well, you first have to construct a Morley tree, and that's going to be our first step. So we're going to first construct a Morley tree, then we'll do Erdős-Rada to find the sequence, and then we'll prove a Kim's lemma for tree Morley sequences, and then we'll be done. So that's the plan. So anyway, what's the goal? We have an anisotropy 1, 3T. We've got a model of the theory. We've got A independent with B over M. And then we want to say that whenever I take an ordinal alpha, I can find a tree indexed by T alpha, which has this kind of funny property. If I look at the top of the tree, the elements that are at the very top level, i.e. those functions whose domain is all of alpha, the full n segment, those look like B. And anything below them, anything that's not at the top will look like A. So anything not at the top will realize the type of A, anything at the top will realize the type of B. And if I take two nodes, one living below the other, if one of them is the top and one of them is on the path below, then the pair will realize the type of AB. So this is a kind of strange condition, but you'll see where this comes up in just a moment. So let's just take this as like, I think it's hard to motivate where this comes from, but it's a kind of technical condition that we need. We're going to build this tree where the B's are at the top, the A's are below. And if you take a pair, one at the top and one below it, then that realizes the type of AB together with being S undiscernible and spread out. Okay, so how do we do that? Well, we're going to do it by induction. And this is the first place where you'll see where this index set comes from. I mean, where it comes from. So, all right. So we're going to build these trees by induction, and then we're also going to somehow assume that all of the trees that I build along the way fit together. So when I described this canonical inclusion, I told you how to put the T alpha tree into the T beta tree. So if I build a tree for T beta, sitting inside of that tree is the T alpha tree, or really the image of the T alpha tree under the canonical inclusion. So I'm going to build my trees in such a way that if I look at the T beta tree and I see something that is indexed by something that came from T alpha, namely something that is in the image of the canonical inclusion of T alpha, then the thing that indexes in the beta tree will be the same as the thing that it comes from indexes in the alpha tree. So like if I look at my tree of tuples indexed by T1, and then I look at the image of T1 instead of T2, and I say, what is that index? It indexes the same tree. So these fit together. It's like a growing collection of tuples. And how do they match? Well, the canonical inclusions tell me how to make this correspondence. So that's just like a kind of coherence condition. And the reason we need that is because at limit stages, what do we want to do? We want to take unions. So we want to make sure that like, it really is the union. So in the model, the collection of things that we're indexing will actually literally be a union. And then what happens at the index set is we take a direct limit. Okay, so that's the first condition that we have to impose. And then we're going to have this other kind of technical condition, which says that, okay, if I take two ordinals, so we have beta, which is less than beta prime, and both are at least 1, which are in alpha plus 1, and I look at two elements on the all zeros path. So one is going to be zeta beta, and the other one is going to be zeta beta prime. And I look at the cone above zeta beta. So zeta beta lies higher up on the all zeros path, because recall the all zeros path goes down. And I can look at the cone above it. And what I'm asking is that the type of C beta over that cone is the same as the type of C beta prime over the cone. So what this is saying sort of is that like the cone doesn't really know its base point. If I look at the cone strictly above zeta beta, if I move farther down in the tree, any one of those will be a candidate for being the base point. Like they all kind of look the same. This is another kind of coherence condition. It says that somehow as I'm moving down, all of these things sort of realize more or less the same type. Okay, so let's get started and just do the first tree. So recall that I'm inducting on ordinals greater than or equal to alpha. So the first tree that I want to build is something indexed by T1, alpha greater than or equal to 1 is what I meant to say. So the first tree that I'm looking at should be indexed by t1. What is t1? That looks like omega to the less than or equal to 1. So I have an empty function, and then I have sort of length 1 node sitting above it. And okay, how am I going to define that? Well, let's start by taking a global M-invariant type, extending the type of B over M. So I take a Morley sequence in B, and because A is Kim-independent with B over M, and I took a Morley sequence in a global M-invariant type, I can move that so that it becomes indiscernible not just over M but over MA. That's what independence gives you. So now I've ended up with this picture here. I've got a sequence of B's, and I've got A at bottom, and all of the things at the top are indiscernible over the thing at the bottom. And so what we're going to do is we're just going to say, aha, that's a tree. So how do you make it a tree? Well, you just define a empty set. You define the root node to be A, and everything above it to be B. Notice that that is spread out, because what is the node that's not at the top? The node that is not at the top is A. And if I look at the cone above it, the only thing in each one of those cones is just Bi, because the cone now consists of one element, or one tuple. And those things are a Morley sequence and a global M-invariant type by construction. That's how I chose the Bi's. So that gives me a spread out tree. And moreover, it's S indiscernible, because S indiscernibility here, what does it say? It says almost nothing. It just says that the sequence at top is indiscernible over the root node. And that's something we arranged. So here, S indiscernibility doesn't actually say much. And that gives us our construction. So that's where we start. And this is like an easy consequence just of A being independent with B. Because A is independent with B in the sense of Kim independence, I can take a Morley sequence in B in the sense of a global invariant type, make it indiscernible over A, and I'm done. Okay, so piece of cake. The base case is settled. Now we want to move on to build the bigger trees. So let's assume that I'm given C beta eta for eta in T beta for every beta up to alpha, and now I want to build the alpha plus 1 tree. So it's a big transfinite induction, and now we're doing the successor step. So we have to make a case division, and this is a bit annoying, but we have to do it. When is the empty set a node? Like, when is the empty function a node in T alpha? Well, that happens only if alpha is a successor. Recall there was this funny, annoying thing about like the starting point could be an element of alpha plus 1, the non-limits of alpha plus 1, because we want to say that you're allowed to have the empty node if the index of the tree, T alpha, is a successor, and if it's a limit, then there's no empty node because there's no bottom. Okay, so if the empty node is in the tree, then you can look at the element of the tree indexed by the empty node, see empty set, and notice that that is going to be Kim independent from the cone above it. Why? Well, this is the argument that we did last time. If I look at the cones above it, that is a Morley sequence in some M-invariant type, which by S indiscernibility is indiscernible over the base node. By S indiscernibility, right? I mean, S indiscernibility tells me if I look at the sequence of cones, it's indiscernible over the stuff below it. So in particular, the starting point of that Morley sequence, namely the cone above 0, must be Kim independent by Kim's lemma. Because Kim's lemma tells me if I can exhibit for you a Morley sequence in some M-invariant type, which is indiscernible over me, then I'm independent from the sequence. Cool, so that means that we have this. And so what we can do is we can apply extension to choose a new element which is independent from the whole tree. So n has the same type. So if C alpha empty node is independent from the cone above it, I can choose something that has the same type, which is independent not just over the cone above the empty node, but the cone above the empty node and the empty node. So I just extend to make it independent with all that stuff. So that gives me A star. Now, on the other hand, if alpha is limit, then I don't have a bottom element. But if I look at this condition that I had above, which I called star star here, that tells me that if I look at the union of the type of C zeta beta, so I look at elements on the all zeros path, and I look at the type that they have over the cone above them, these types all fit together, actually. Because the type of C beta over the cone above it is the same as the type of C beta prime over that cone, is the same type as C beta prime prime over that cone as I move farther down. So all of these types are extending one another. And that's a kind of coherence condition. So that means I can take the union, which is some infinite union of types. Every finite piece is consistent because it's realized by one of these elements along the all zeros path, and therefore it's a consistent type by compactness. So I can realize it. And by construction, I knew that each piece along the way was independent with everything above it by what we did in the successor stage. So it follows that a realization will be independent from the whole tree, right? So if it depends, then it will depend with only finitely many parameters. Those finitely many parameters will appear in one of the trees in the union, and then that means that something on the all zeros path will depend, because this is just the union of the types of the all zeros path. So so in either case, I could choose an A star, which is independent with the whole tree, and realizes the type that I see along the cones on the all zeros path. Great. So now what do we do? Now we're going to take a type Q, which is a global and invariant type, extending the type of the whole tree. So this is a type in many variables. So I take a type, extending the type of the whole tree over the model, and I take a Morley sequence inside that type. So what am I doing here? I'm taking countably many copies of my tree, which are moving along in a Morley sequence. So the way I'm going to index those is I'm going to call it C alpha eta I, and so each tuple, which you should think of as like depending on I here, is like a copy of the tree. So as I varies, I'm looking at different copies of my tree. And I want to, so now I've taken a whole bunch of copies of my tree, and I want to add something at the bottom. What should I add at bottom? Well, A star. That's the A star I picked. So we can assume that this collection, this Morley sequence that I've taken is, because we chose A star so that it was independent with the tree, and we took a Morley sequence starting with the tree, we can assume that Morley sequence is indiscernible not just over the model, but over the model and A star. That's what independence gives you. And so we'll do that. And then we're going to define a tree d eta in sort of the natural way. So what is our new root node? That's going to be A star. Notice that now we're at a successor stage, so we have something at the bottom. And then if I want to say, okay, what happens when I go in the ith direction and then go eta? That's like looking in the ith tree and then looking at the thing corresponding to eta there. So what happens? Well, I first look at my tree T alpha. That's what I have here. That's step one. That's just what induction gives me. Step two is I look at eta and I choose some new root node, which is A star. So we had two arguments for how that happens, that it can happen in the successor stage or in the limit stage, depending, we had two different arguments in those cases. One was just by extension, the other one was by union and this condition star star. Then three was, I took a Morley sequence. So I need to figure out how to turn off this sound, because it's very loud. It's not even showing on my screen. There's no indication. Well, that's frustrating. Okay, I hope that fixes it. But yeah, it's just a spam call too. It's like someone calling from like a 417 area code telling me that my social security number has been suspended, and then I'm going to go to jail. Okay. Great. So I was explaining the procedure. We start with our tree. We choose a new base point, which is independent from the whole tree. We take countable unit copies of our tree, which are moving along a Morley sequence. We can assume that that's indiscernible over the new base point using independence. And then we construct a tree. So how do we construct the tree? Well, we define the new base point to be the new base point. And then we say, okay, how do I define di concatenated with eta? That's the element corresponding to eta in the ith copy. So that gives you a tree. So you can sort of see the picture here. We just sort of view this picture as a tree indexed by one bigger ordinal. All right, now that's great. That tree is certainly indexed by t alpha plus 1. It is spread out, which you can easily see by construction. We made it spread out. The question you might worry though is it S indiscernible? And many a good model theorist have asked me if it's automatically indiscernible, because it seems very clearly like it should be. But in fact, it's not necessarily indiscernible in the S indiscernible sense. Why? Well, okay, you do know, for example, that like this sequence here is indiscernible over this. But what you don't yet know, for example, is like, is this sequence indiscernible over this pair? And you don't know that. We certainly didn't ask for it at any stage in the construction, so we don't know. There's no reason to believe that happens automatically. So what we have to do is actually replace our tree with an S indiscernible one using the modeling theorems. So what we'll do is we'll take our tree, which is indexed by t alpha plus 1, and we will define c alpha plus 1 to be an S indiscernible tree locally based on the d eta tree that we just built. So all you do is you sort of take the tree that you build and you make it indiscernible. But because everything is sort of in the right type and has the right relations, everything is probably pretty close to indiscernible. All the conditions are still satisfied. So that will still satisfy all the requirements. Everything will still satisfy the same type. Well, okay, not literally everything. Obviously, the tree itself has different types, but the individual elements in the tree will all satisfy the same type. And the relation between the top and anything below it will still be preserved, as well as being spread out. All of these requirements are still satisfied. So that gives you the next tree. And that tells you how to go on one more step. So that handles the base case and the successor step. And then what do you have to do at limits? Well, at limits, you take unions. And what does it mean to take a union? Let's just define it properly at least once. So if we're given C alpha eta in T alpha for every alpha less than delta for some limit ordinal delta, we want to get the tree indexed by T delta. How do we do that? Well, suppose you want to define C delta on an element which is in the image of the canonical inclusion of T alpha into T delta. So I have some eta in T alpha, and I look at its canonical inclusion into T delta, and I want to say, okay, how do I define that tuple? And what I'm going to define it to be is just the alpha, the element corresponding to eta in the alpha tree, right? Because I wanted exactly this coherence condition. So I'm going to define it that way. I'm going to say, okay, if I take an alpha less than delta, and I take some eta in T alpha, how do I define the tuple indexed by its image under the canonical inclusion? Well, I just defined it to be the same element. I defined it to be C alpha eta. Now, the problem is that you have to check that is well defined, because there could be elements of T beta that are in the image of more than one canonical inclusion. You could take something which is the canonical inclusion of something in T alpha, and then that could also be a canonical inclusion of an element from T beta. But the point is that the canonical inclusions all fit together into some kind of system, right? Like if you take an eta, which is in T alpha, the canonical inclusion into T delta is the same thing as first canonically including into beta and then including into T delta. Why? Well, because what does it mean to include eta into the beta tree, I just extend by zeros until I make the domain beta, or an in segment of beta. How do I include into delta? I just extend by zeros until I get to delta. Okay, if I take a pit stop when I'm extending to delta at beta, then I haven't really changed what I'm doing. I've just extended by zeros in 2 steps. So these things all cohere, it fits together. And this is like a well-defined way of giving you the delta tree. So on the index set, we're taking a direct limit, but actually in the model, what we're doing is we're just taking a union. These tuples are a union. So that gives us the tree that we want. So now we're going to produce the kind of sequence that we were looking for. So we built the tree, now we need the sequence. Suppose T is in SOP1, you have a model of your theory T, and A is independent in the sense of Kim independence with B over M. Then there is an MB indiscernible tree Morley sequence over M starting with A. So this is exactly like the lemma we had in simple theories, where we said if A is forking independent with B over M, then there's a Morley sequence over M, which is MB indiscernible and starting with A. So good. How do we do that? Well, let K be large. And what do I mean by large? I mean large enough to apply Erdos-Rado. So Erdos-Rado said there is a cardinal relative to, which depends on the cardinality of M, so that if I'm given a really large tree, I can make one which is based on it and has this property that no matter where I look vertically in the tree, I always get the same answer. So we will apply the previous construction to produce a really tall tree indexed by T kappa, which is S indiscernible spread out over M, and has this property that if I look at some nu, which is an initial segment of eta, and eta is at the top of the tree, then the type of the pair C nu C eta is AB over M. So this is like what we had before. So now this is a kind of funny tree. We've got one thing happening at the very top, and then we've got below everything just looks like A, right? So what we can do is we can just say, for a moment, let's just forget the top. So I have a tree indexed by T kappa. What happens when I delete the top? So now I'm looking at functions which are defined on an in segment of kappa, where the in segment must start at least at 1, or I guess, yeah, at least at 1, right? It can't start at 0 because I've removed the top element. All right, but okay, if I look at the set of functions which are defined in an in segment of kappa starting at 1, that's like clearly in tree partial order preserving by ejection with T kappa itself, right? Like if I take the ordinal kappa and I remove 0, that's still the ordinal kappa. I mean, it's not literally the same, but it's order isomorphic to it, right? So certainly the tree T kappa is going to be, isomorphic as a tree to the tree that I get by taking T kappa and removing the top. So I'm going to remove the top, call that T prime, and I'm just going to renumber my sequence. I'm going to renumber my tree that I get by removing the top as C prime eta in T kappa. So I'm just pointing out that you can index it by T kappa. Okay, now all of those things realize the type of A over M. That was how we built the tree. At the top, you realized B. Everywhere below, you realized M. You realized A over M. And by Erdos-Rado, we know that we can extract a tree, which I'm going to call A eta in T omega, which looks very much like the tree that we built before. Great. So now let Pxy be the type of B A over M. So the B's are in the X variable, the A's are in the Y variable. And what we want to do is we want to look at the type of B along the all zeros path in this new tree that I build. And I want to say that I can realize that. So of course, by compactness, it suffices to show that it's finitely satisfiable. So I can look at just maybe the first n along the all zeros path and find some B that matches with all of these things. So choose some subset in the non-limits of kappa such that if I look at the type of A eta, eta and T omega restricted to just the first n-1 levels, or really the last n levels, so 0 to n-1, that has the same type as the restriction of C prime eta, eta in T kappa restricted to V prime. Why does that exist? Well, that's what Erdestrado told me, right? If I have a type of a restriction of the Morley tree that I built, that comes from a restriction to some number of levels in the big tree. That's this kind of basedness fact. So because these types are the same, it actually suffices to show that actually this union is consistent. If one is consistent, the other is, because these are the same. I mean, the parameters have the same type. Okay, but that is realized by this thing that's at the top of all of them, the C zeta 0 without the prime, because that looks like B with respect to everything below, right? So what is it that we want? We want to say, I have these nodes which are living on the all zeros path in the really big tree that I built. And what do I want to find? I want to find some element that looks like B with respect to all of them. But the tree that I built had this property that if I take anything at the top and anything below it, the type of that pair will say that the thing at top looks like B and the thing at bottom looks like A, and together they look like AB. So the thing at top will look like B with respect to everything on the path below it. And so it's going to realize this type. So that means that we can find some B prime that realizes this union. So with respect to everything on the all zeros path, it looks like B. And everything on the all zeros path looks like A. So together they look like A. They look like AB. They all realize the type of AB over M. They all realize P. Okay, so then extract a indiscernible sequence. So by Ramsey compactness and an automorphism, I can assume that A zeta I less than omega, is MB prime indiscernible. And then because B prime A zeta 0 realizes the same type as BA over M by the choice of P, I can move the sequence by an automorphism and assume that B prime equals B and A zeta 0 equals A. So after moving by an automorphism, I can assume they're the same, and then that gives me the thing I wanted. That gives me a tree Morley sequence over M, starting with A, which is MB indiscernible. Okay, that's the hard part. So this argument is complicated, and you have to really squint to sort of see that this is the same thing as what's happening in simple theories. The problem is just that you need it to be not just indiscernible over MB, but you need it to be very generic as well. So you have these sort of two constraints that you have to juggle at the same time, and this is the way we figured out how to do it. So let's just look at this picture once more to remind yourselves how this goes. So you have T kappa, which is this very big thing. You look at the top, which all look like realizations of the type of B over M. Everything below it looks like a realization of the type of A over M. From the blue box, you extract something that looks like a tree, like a Morley tree, a proper Morley tree. And the fact that it came from this big tree in the way made precise by Erdestrado means that the type of B along the L0's path is consistent. Okay, so that gives it 2. Cool. So in particular, if you have any element over a model, there's a tree Morley sequence starting with that element, which is nice. It's good to know. There are other ways of seeing this, but the other ways of seeing it come from just showing directly that an invariant Morley sequence is a tree Morley sequence. So that's nice. Great. So now we have one more thing to do, which is to prove Kim's lemma for tree Morley sequences, and then we will have a proof of symmetry. So this one actually is not so hard, thankfully. So let's assume we've got an NSOP1 theory and a model of the theory. The following 3 things are equivalent. One is that you have a formula that Kim divides over M. 2 says that formula is inconsistent along some tree Morley sequence. And the third condition says that it's inconsistent along every tree Morley sequence. So it's exactly like the Kim's lemmas that we've proved before. And how does this go? So take your arbitrary tree Morley sequence over M. So we're going to call that I, AI less than omega. And okay, that's a tree Morley sequence. So it is the all zeros path in some Morley tree. Let's fix the tree. Call it A eta, eta and T omega. And so we have this correspondence that A zeta I corresponds to AI. The ith element along the all zeros path is the ith term in my sequence. Now we're going to look at some other sequence. So xi will be defined to be zeta I plus 1 concatenated as 1. So what does that look like? It looks like, take zeta I plus 1. So that's like you start at the top and you go down I plus 1 many steps, and then you go up by 1. So I've drawn this picture here. So in green, you see the xi's. So what does xi look like? At xi0 is your 1 at 0, and then you're 0 everywhere else. What is xi, or sorry, that's xi0. What is xi1? You're 1 at I guess 1, and you're 0 everywhere else. What is xi2? You're 1 at 2, and you're 0 everywhere else, and so on and so forth. Great, so that gives you these elements. And what's awesome is the spread outness condition tells me what? It says that, okay, xi1 realizes a global M-invariant type over xi0. Because xi0 is in the cone starting at zeta 1, right? Like if I look at the cone above this element, and I look at the cone above this element, I know that these differ by a global M-invariant type. Like one realizes a global M-invariant type over the other. That's what spread outness says. So in particular, xi1 realizes a global M-invariant type over xi0. They're invariant in that way. And likewise, xi2, which lives in this cone, will realize a global M-invariant type over this cone, which contains both xi1 and xi2. So what does that mean? It means that they're independent in some sense. And this couples with the fact that these xi's form an indiscernible sequence using the fact that you can move vertically in the tree to say that the xi's are a Morley sequence in some global M-invariant type. Indiscernibility plus independence will tell you that. So what do you know? Well, you know that a formula will Kim divide if and only if it is inconsistent along the tuples indexed by the xi's. That's what Kim's lemma for Kim dividing tells you. Kim's lemma for Kim dividing says that if a formula Kim divides, that's witnessed by any Morley sequence in a global M-invariant type. And we found inside of our tree a sequence like that, namely the sequence of the xi's is a Morley sequence in some global M-invariant type. This is what spread outness gives you. So that is like bonkers. I mean, it's really unclear what this whole spread outness thing is trying to accomplish, but actually this is what it gives you. What it gives you is that you've got this sequence of xi's, which are just off the all zeros path, and those are a Morley sequence in some global M-invariant type. And so those witness Kim dividing if your formula Kim divides. But then S indiscernibility tells you that if I look at A xi and A zeta I over everything that comes below in the tree, those things have the same type, right? That's what S indiscernibility will tell you, that somehow these two things, which I've drawn in blue here, those two things have the same type over everything that comes below them because of S indiscernibility. Those two things have the same type in the S tree language. So what does this look like? We've got two columns, and every element in the column has the same, at any row, those two elements of that row have the same type over everything that comes below. That looks an awful lot like the SOP1 array that we studied. So suppose that you have a formula which is consistent along one side. Well, if it's k consistent along the other side, then you get SOP1. That's what the array condition tells you. If you have a sequence of pairs and a formula that is k consistent along one side and consistent along the other side, and at any row, those two things have the same type of everything that comes below, that's what it means to have SOP1. So you know that your formula is going to be consistent on the left side if and only if it's consistent on the right side, because you have assumed that your theory is in SOP1. Okay, and then that does it, right? If you have your formula that Kim divides, then it's going to be inconsistent along the green sequence by Kim's lemma. Therefore, it must be inconsistent along the left-hand side along the zeta i's by the configuration that we just found. So that means that if you Kim divide, then you have to be inconsistent along the sequence, and that sequence was an arbitrary tree Morley sequence. So that says that if you Kim divide, then that's witnessed by any tree Morley sequence. Conversely, if you do find a formula that is inconsistent along this tree Morley sequence, then it must be inconsistent along the associated invariant Morley sequence. Then by Kim's lemma, that, or actually just by definition, that implies that it Kim divides. So that gives you all of the implications. So that gives you Kim's lemma. So I think this is like really surprising, actually. I mean, you have this funny combinatorial definition involving sequences of pairs. You build this tree, which seems like it's coming out of nowhere. And then lo and behold, what you find is exactly the tree configuration. I mean, the array configuration where one of the rows consists of a Morley sequence in a global invariant type. And that's amazing because you know exactly how your formula behaves with respect to those. If it Kim divides, then it's inconsistent along that sequence. And if it doesn't, then it's consistent. So that tells you correspondingly exactly how your formula behaves with respect to tree Morley sequences. So now all we have to do is just take it to the hoop and prove symmetry. How do you prove symmetry? Well, it's a piece of cake. So we want to assume that our theory is anisotropy 1 and conclude that Kim independence is symmetric. So let's do this very quickly. You've got theory T, a model of your theory. A is Kim independent with B. By the proposition, we can produce a tree Morley sequence starting with A, which is MB indiscernible. So that's what we did. Now, suppose towards contradiction that there's some formula phi x A in the type of B over MA, which Kim divides. Then that's going to be inconsistent along any tree Morley sequence by the Kim's lemma that we just proved. However, by indiscernibility, we know that B realizes all of those formulas. I mean, it looks the same with respect to all of them by indiscernibility. So if you have something which is in the type of BA, then it's going to be in the type of BA1 and BA2 and BA3 and BA4. So B realizes that all of those formulas. And by Kim's lemma, that means that it can't Kim divide. Because if it did, then that would have to be inconsistent and then it can't be realized. But that was any formula at all. So that means that B is Kim independent with A over M, and Kim independence is symmetric. So we did it. Great. So I think, one thing that is exciting about this argument is that it shows you there's really some theory here, right? You really have to use the properties of the dependence relation in an essential way. You really use the Kim's lemma, you use extension, and using that theory, you can conclude something. But it would be really hard to argue directly from the combinatorial definition to seeing that Kim independence is symmetric. I don't know how to do that. So this tells you that actually, I mean, there's some gain in thinking about Kim independence, developing this theory. You learn new facts about the theory that you couldn't have seen just working with the formulas and trees and arrays and hoping that playing games with formulas would get you there. It's not clear that it would. So for me, this is sort of like a vindication of the study of Kim independence. You get something out of it, but obviously it's complicated. And this is only just like a taste. All right, I think I should stop there. I've gone almost 5 minutes over, so I'll stop. Are there any questions? No? All right, so next time we will switch gears and we will start talking about NTP1 or NSOP2 theories. And there's a nice theorem which is not much studied. I mean, I think many people in model theory don't know it, which characterizes NTP1 in terms of having having a bound on the size of a configuration which is called k-inconsistent higher formulas. So this is something I've already written down, and so I'm going to write over the weekend notes for the NSOP1 stuff, and then I'll just include those. So feel free to check that out. The notes for everything up to NTP2 are posted, by the way. So feel free to look at those. And yeah, enjoy your weekend.